The Somalia Space Workshop is happening. So in the next 15 to 20 minutes, we will discuss food production in closed loops for space and how these has implications for Earth. So my name is Lucie Poulet and I come from France, but I'm currently living and working in Florida at the NASA Kennedy Space Center. And to start these, I will introduce myself briefly. So, as I said, I'm a researcher at the Kennedy Space Center, a postdoc, so that's something that I do after having defended my PhD, after my doctorate degree. And I study plant behavior in space, especially gas exchange and how plant gas exchange behave when the gravity is lower than Earth gravity. And so my background is aerospace engineering and physical and chemical process engineering. And I have been working for over 9 years in the field of life support systems with different space agencies, among them, so NASA now, but also the European Space Agency, the French Space Agency, and the German Space Agency. And I've participated in 4 Mars analog missions, and that's the photos you see here on this slide. And a Mars analog mission is a simulation mission, a simulation of a Mars mission, and I will detail that a little bit later here. So first, to start, some context about space exploration as it is now. We have the International Space Station above our heads that is located 400 kilometers only above us. In the International Space Station, astronauts live there and they live there permanently. They rotate, but there is always someone in the International Space Station. And they depend on Earth for the resupply. So Earth sends them food, water, supplies, scientific equipment, all what they need to live and work in this space laboratory. If there is a problem from the International Space Station, they can come back as fast as in 6 hours. Now, the current plans for the future of exploration is to be back on the moon, at least for NASA, in 5 years. And ESA and China are also having as the goal to go to the moon, but they haven't said in 5 years. And from there, from the moon, then using the moon as a stepping stone, the idea is to go to Mars. The distances are really not the same than what we have on the International Space Station. The moon is 1,000 times further away from Earth than the International Space Station, and then Mars is 1,000 times further away than the moon. It takes 6 to 8 months to go to Mars, and we have to choose the window, the time frame, to go there very wisely, because if we don't pay attention to that, the trip will be way longer and we'll use way more fuel. So we can go to Mars in 6 to 8 months, every 2 years roughly. So when we think about these distances and these duration of missions, we have to think differently. We can't only rely on Earth supplies to survive in a long duration mission on the moon or on Mars. We need to keep the astronauts from a mental point of view, but also from a physiological point of view, when they get to Mars, when they stay on Mars, and then as they come back. And so in these contexts, 5 years ago, I participated in a mission, in an analog mission in Hawaii, on a volcano that is called Mauna Loa. And so that's a closer, like a zoom view of where we were. I spent with 5 other people 4 months in this white dome. The main thing of an analog mission is to be in a Mars-like environment. So here on this volcano with red volcanic rocks, this really looks like a Mars environment. And we need to be isolated from any human, plant, and animal life, and that was the case here. We were really far away from any sort of civilization. Now, we didn't stay all the time inside the dome. Sometimes we would go out, but to go out we had to wear a spacesuit. So that was not a real spacesuit, that was a spacesuit that was specially made for this mission. So it's a spacesuit that cannot be used in space, but it was heavy enough and bulky enough to simulate the constraints of walking with a spacesuit. Now, other constraints and specificities of these habitats were the resources that we had. The water resources, for example, were very limited. The tanks that are circled on this photo are on the right side are clean water tank, potable water tank, and that was resupplied every 4 weeks by our mission support. And with the amount of water we had, we were limited in the lengths of showers we could take. So we were limited to 8 minutes per week. My personal average was 4 minutes per week, so that means a shower every 2 to 3 days, which would last about 1 minute to 1 minute and a half. And we had dry toilets, and then we would be very conservative in water for washing the dishes or washing our clothes. The left water tank, that's our wastewater, and this was collected every 4 weeks, about every 4 weeks as well. In terms of energy resources, so you saw it on the previous pictures, and now you see it a little bit closer. That's solar panels, and that was our prime source of energy. So we were relying only on, mostly, let's say, on solar panels to get our energy. That meant that we would adapt our day-to-day activities to the amount of solar power that we could get. So if it was a cloudy day, we would not eat a warm meal at night, and we would really limit the use of all the energy like the equipment that use a lot of energy. For example, the treadmill, because we had a treadmill to do some sport, we would not use that on a cloudy day. So that's example. So we were really living with limited resources, but also we had to, these resources in energy, for example, it would vary from one day to another, depending on the solar energy that was getting in. So we really needed to adjust our behavior according to the resources we had. In terms of food, that's a photo of our food for 4 months. Here we were sorting out all the food we had, putting them in certain boxes for month 1, month 2, month 3, month 4. That's shelf-stable food, so it's food that can stay good for many years at room temperature. It will not go bad. So it is freeze-dried food. Freeze-dried food is food that is dehydrated, basically. But we also had things like pasta or cookies or rice that they're not freeze-dried, but they can stay on shelf for a very long time. The reason for having these food is that currently on the International Space Station, the food that astronauts eat is food that is either freeze-dried, either all prepared, like canned food, all prepared, and they just need to eat from it. Very limited amount of preparation, very limited very limited weight as well, because they cannot bring that much weight to the International Space Station. So we had all this food to sort out, and this is a close-up of how the vegetables looked like. So you had tomatoes, bell peppers, and onions on this picture. This meant that in order to use them, we had to rehydrate these foods, and then we were able to cook them. In terms of taste, it was very similar to any vegetables that we had in our daily life, but in terms of texture, because they were rehydrated, they were very mushy. Nothing was crunchy like a vegetable that you would bite in. So that was problematic for some of my crew members, my crewmates. Some people after 4 months were really tired of having a texture of food that was always the same. You know, the taste could be different, but the texture was always the same. And so luckily, we were also growing some plants. We were growing lettuce, radishes, some cherry tomatoes, and some peas as well. And the quantity we were growing was not a lot. We had about 1 plate of lettuce and 1 or 2 radishes per person per month. But as you can tell from the face of my crew members, everybody was really happy to have fresh food, even if it was once a month. And the reason for that is again the texture. Fresh vegetables don't taste the same first, but they don't have the same texture as rehydrated food. And that really brought a diversity into our diet and into our day-to-day life. And that was very important to have that. That's how it looked like. So it was really an experiment. We were not growing food for, we were growing a little bit of food for the sake of growing food, but the majority of it was actually part of an experiment. And you see that on this photo, I'm looking at different colors to grow plants indoors. And that's something that is really studied a lot for controlled environment agriculture. So the agriculture that we do indoors using this type of light, which is very studied for space exploration, of course. So that was an experiment that I was having here, and the reason why we do these experiments and why we measure how much we are getting out of all of these different experimentations is because if we use biological organisms like plants to feed the astronauts in space, we need to know how much we can get from them. And that's why we do calculations and why we have measured how much a person needs per day. So we have to go back to the basics of that. So per day, any person, astronaut or not astronaut, I just put an astronaut here to be in the topic, but per day, a person needs 800 grams of oxygen, 3.2 grams of water, 600 grams of dry matter. And then as waste, we generate 900 grams of carbon dioxide, 3.6 kilograms of water, and 100 grams of dry matter. And so all of this, if you do the sum of these two sites, we have about 5 kilograms coming in and 5 kilograms coming out. So if you do the math for a 1,000 days mission, 6 people, and a 1,000-day mission, that's the standard time for a mission to Mars, these adds up being 30 tons that we have to bring to Mars for only breathing and eating and drinking. Not even talking about taking a shower or washing your clothes or all the experiments that people will have to do, all the experimental equipment that will be needed. and all the other infrastructures. So because all these mass that we have to bring to Mars or to the moon, if we want to do long duration missions, we need to think about a system that can regenerate the air, recycle water, treat wastes, and produce food. And we need to have this system in a confined environment. We need to create a closed loop. And this idea of closed loop is very much studied into the space agencies around the world. The European Space Agency has been studying closed loops for over 30 years now with the project called MELISA. NASA is looking at closed loop systems as well. Roscosmos in Russia as well. China a lot with their lunar palace. All the big space agencies around the world look at that. Basically, the idea is really, can we recreate an ecosystem like on Earth, but artificially in a spacecraft? Now, these functions here, like regenerating the air or recycling water or treating wastes, these can be achieved by physical-chemical processes as well. It doesn't have to be achieved with biological processes like on Earth. On the International Space Station, right now, the water is recycled and the air is regenerated using physical-chemical processes. But if we want to grow food, to produce food, we have to use biological processes. We don't know how to do it otherwise. And so that's what we are really working on here at NASA. We are studying how to grow food on the International Space Station. And so there is a system there called veggie, where we grow leafy greens almost permanently. There is an experiment stops and then another experiment starts. It's been like that for 5 years. Mostly the vegetables that are grown there are leafy greens, so green vegetables that you can use in salads. So it's just a food, a supplement food. It's not a whole diet food, but it's a beginning. We're still learning how to grow food in such an extreme environment because the physics there is really different in terms of fluid movements, and it makes watering the plants very challenging, for example. And all of these principles of growing plants indoors and recycling water, regenerating the air, these, as I said at the beginning, have applications for Earth, So what you see on the left side, on the top of the slide, is a drawing of the biosphere technology that was developed by a company, a spin-off company from the MELISA project from the European Space Agency. And this biosphere technology has been used in Europe for water treatment a lot. And then, inspired from the water treatment process that is used on the International Space Station by NASA, other purification system for water and water treatment systems have been installed in several countries around the world. Here the examples are Iraq and Pakistan, but they also installed this system in South America for purifying water, and that's using technologies developed for the International Space Station. Now the drawing you saw on the bottom, that's a sanitation unit for water, that could be used in places where extreme events have happened, like a natural catastrophe, like a war, or if it's just in a very extreme environment, like Antarctica or a desert. And this comes from a whole concept of a closed habitat that would be powered by solar panels. There would be a living area, and this living area would be linked to a sanitation unit that would collect the gray water, black water, yellow water, all the wastewater, and treat all this water, recycle the water, and recover the nutrients that are in this water, and then use all of these to feed plants in a food production unit. And then this container would be independent and could be used to relieve zones that have been struck by very extreme events. So that's the kind of applications and technology spin-offs that we are working on, based on the technologies that have been developed for space exploration. So I think I'm out of my time already, so I want to thank you, and I'm happy to welcome any questions you have.
Thank you very much, Lucie. We appreciate your presentation. It's really inspirational. I'll double check if they have any questions. We'll see. سؤال ما دوسنا ويديسين ناسي كشق يسألك سؤال كستو دونس ويديسين أو ويديني كتير بدو التخصص يرفعها ترى إنك بالطاقة عرك لودل والله يكون مقنعان عرك لح بلودل أصلا ترى إن وحلودل لحلي بلود مر كماها دليفري وترى دوتد تراجع على هذه سجارة المسين ترى والله سيدي يا ريال تانا حتى التكنولوجيا اللي فائدة في ليرها عبارة داعي لأن مرمر لما قال يكرو ويك ماشي عم بحال عكتا ماشي عبارتك دعيني لح بلوضة لح مع المود نطابق كسب سمع مكا وحا أصلا حتى التكنولوجيا لاس وحا حتى فائدة كيني كرا يوم هذا إذا عمتنا production care سي efficient لو سوساني يا حتى نفاسين كرا حتى قرا المقولة حاجة ندين عنا وحالنا قرية ندين عنا يدنا يدنا وحيرين وحيرين وكذا يدين كسؤال ودونسين ويسين ويدين سؤال دوا شورينا وچانس ها ادو ترجمه ودي واي marka dadka kuma xiiga maxaa soo faqray kawar garaaf tuuleeyay sidoo kale waxay sameeyaan maxaa hore exercise fara اللي فوق لفها يو مقياشه يا ka dhamaanay صوت جرافيتي لا هي حاجه كوره soo jiidsa laakiin صوتك wixii ka caawin sarta lafaa iyo maqyasha جيك مركز عادي يكون باسمه حقا لكن جرافت هذه يرتب أداء أردو أداء أنت الساعات توبر سمينه لفهاري ومقياش على بعضها ما كان عندك سواء كان وطاس مش صغر محمد محمد ويلسا بالون حوية ونحن ترون حوية حتى عندنا حوية. So have you heard someone that wants to ask? Obviously you kind of already know, but the physiology side of the things, how that affects the human body, because the gentleman he is a little bit shy to ask, but I will ask for him. He's basically asking, so you know when astronauts go to space and they stay there for a long time, it has effects on their heart, it has effects on their vision and their eyes. So obviously because this is very new to them, they don't know that information as of right now yet, but maybe you can explain a little bit more to them, and also the fact that this food, like for example to the ISS, they receive it maybe once in 6 months or something like that, supply, like you mentioned earlier.
So you want me to talk about the effect of microgravity on the human body? That's what you're telling me?
Yeah, maybe you can give a little touch on it, because obviously it's not your expertise, but you can just say how because I know you mentioned like it's mostly you're into like the food production side of things, but they wanted to understand as well how that how space microgravity affects the human body.
Okay. I just wanted to double check if I understood well what you said. Okay, cool. So when you're in microgravity, several things happen. First, you don't weigh anything because you're free falling around the Earth permanently. That's the principle of being in microgravity. And because you don't weigh anything, your muscles and your bones won't have any function anymore. And we often say the function beats the organ. And so if you don't have a function anymore, you lose the organ. So what happens if the astronauts stay 6 months in the International Space Station and they don't do sport, they don't exercise, they will little by little lose their muscle and they will have osteoporosis. Their bones will become porous. Now, the astronauts on the International Space Station, they do 2 hours of sports, of workouts per day. Every day, there is no break for the weekend, so every day, 7 days a week, they do 2 hours of working out, and they do that if they stay 6 months, 5 months, or 2 weeks, or a year. They have to do it, and when they come back on Earth, even with all these sports, they lost some muscles. Usually, they have lost muscles. Their bones are a bit more fragile. So that's something to keep in mind for people who will go to Mars, for example. They will have 6 months of microgravity and then several months of reduced gravity. The gravity on Mars is 40% of that of Earth, and then another 6 months of return trip in microgravity. So we need to think through how to maintain the human body in a good shape through working out. Then what happens as well is that your heart on Earth is used to pumping a lot of blood so that the blood comes back from the legs and goes in the head and goes in every part of your body. But if you are in microgravity, it's different, but your heart doesn't know it and still continues to pump a lot of blood. And so the astronauts, if you see pictures of the astronaut on the International Space Station compared to pictures on Earth, their face is very puffy because all the fluids go back in the upper body because of these heart pumping a lot. And so what they have noticed on certain astronauts, not all of them, is that they can have pressure on the optical nerve on the eye, and they come back and they have lost some visual acuity in their eyes. So, and that's not reversible. That's some things that happen. Then this heart thing. This means that if you imagine having a baby that will be born on Mars, probably the heart of the baby will be adapted to the gravity of Mars, and so will be pumping only for that gravity. And then if you come back, if you bring this baby to Earth, this child to Earth, their heart might not be adapted for higher gravity and might have problems. So yeah, the human body is really adapted to its environment, and putting it in a different environment means a lot of adaptation, and we need to understand that. But it's also a great way of people to do medicine experiments and understand how things evolve in the International Space Station, because they have a lab that is gravity-free in space, so they can study a lot of different mechanisms of the human body. I don't know if that answers a little bit question.
One second.